Good morning, teacher, and hi everyone. Today we are going to introduce conic section. And let me introduce our group. Our group name is NTW, and our group member is Neo Sun Hong and me and Wong Yong Hearn. We are from the section 22. So let's talk about conic sections. So basically, conic sections are the curve obtained as the intersection of a plane with a cone. Okay, so there are four types of conic sections, and which is circles, ellipses, parabolas, and the hyperbolas. This is the formula of the conic section in the origin. So why do we use the conic section? The conic section helps us to solve the real-world problems in the field like physics, engineering, astronomy, architecture, and so on. So they formulate complex problems into simpler and manageable forms. Conic section of the circles. Circles are a type of conic section that we encounter daily. So they are used in the design and architecture due to their symmetry. So for example, the wheels of your bicycle or cars are circles. The round shape allows smooth and efficient movement. Is all about the conic section of the circle.
Now I will continue with the second conic sections, which is ellipse. Ellipses are another type of conic section. They are used in astronomy to describe the orbits of planets around the Sun. The elliptical shape of these orbits is due to the gravitational pull of the Sun and the planet's velocity. Next is the parabolas. Parabolas have a unique properties that makes them useful in many fields. Any object projected in the air follows a parabolic path due to gravity. So this principle, we will use it in sports like basketball and in engineering fields for designing bridges and antennas. Next is the hyperbolas. Hyperbolas are used in navigation and radar systems. The property of hyperbolas helps in determining the location of an object in relation to two fixed points. This is crucial in GPS technology. Second part, we will present about the real-life conic section application examples. Liang Yao said there is many real-life applications of conic sections. Now I will explain one of them, which is physics. So in physics, conic sections are used to describe the trajectory of projectiles, and this is crucial in fields like ballistics, sports, and even space travel.
Conic sections in engineering. In engineering, conic sections are used in the design of various structures and machines. For example, the reflectors of headlights and torches are parabolic. This shape helps to focus the light beam in a particular direction. Conic sections in astronomy. In astronomy, the orbits of planets and comets are often elliptical. Understanding the properties of these conic sections helps astronomers predict the movement of this celestial body. Conic sections in architecture. Conic sections are widely used in architecture. The arches of bridges, domes of buildings, and even the design of fountains often incorporate elements of conic sections that provide both aesthetic appeal and structural integrity. So the problem statement 1. A satellite is orbiting the Earth in an elliptical path. The semi-major axis of the ellipse is 10,000 kilometers and the semi-minor axis is 8,000 kilometers. What is the equation of the ellipse? So from the question, we know that the length of semi-major axis is 10,000 km and the length of semi-minor axis is 8,000 km. So we represent the semi-major axis as A and the semi-minor axis as B. So now we're gonna sub a and b into the equation of ellipse. So the equation of ellipse is x squared over a squared minus by y squared over b squared equals to 1. Therefore, we get x squared over 10,000 squared minus by y squared over 8,000 squared equals to 1.
With the second problem statement, a cell phone tower is located at the coordinate of 5, -2 brackets on a coordinate plane with units be kilometers. What is the standard form of the equations of the outer boundary of the region serviced by the tower if it is designed to service a 10 kilometers radius? Is a subscriber at the coordinate of 7, 8 bracket within the service range of the tower? So let's see the solution. Firstly, I will find the standard equation of the circle, which is x minus h bracket square plus y minus k bracket square equals to r square. So from the formation, we knew the radius r equals to 10, which means the standard form of the circle is x minus h bracket square plus y minus k bracket square equals to 100. Next, the cell phone tower is located at coordinate of 5, -2 bracket. 5 and 2 is represented as h and k. Thus, we can get x minus 5 bracket square plus y plus 2 bracket square equals to 100. To find whether service range, we just simply sub the coordinate 7, 8 brackets into the standard equation and see whether the answer is higher than 100 or not. Finally, we can get the answer is 104, and it is obvious which is not in the service range at coordinate 7, 8 bracket. So this is the final solution.
Alright, so let's see problem statement 3. The cable of a suspension bridge are in a shape of parabolas. So the towers supporting the cable are 1000 meter apart and 200 meter high from the ground. So what is the height of the cable at a point of 200 meter from the center of the bridge if the lowest point of the cable is at a height of 40 meter midway between the towers? Okay, so we can see I already draw a graph about the suspension bridge, and then we can know the minimum point is 0, 40, so which is our vertex, and then we want to find the height of the cable at the point 200 y. So we know that the parabola of the equation is x minus h squared equal to 4p y minus k squared. So we just simply sub the h and k into the equation of parabola, and then we got x minus 0 square equal to 4p y minus 40 square. And then we found out the G point is at 500 and 200, so we just simply sub in it and we found the 4p. And then lastly, we just sub the point 200 and y into the equation of parabola, and then we found that the y is 65.6, which is our height, and then the problem solved. Thank you.
So the conclusion of conic sections. Conic sections are fascinating mathematical tools with vast applications in various fields. Understanding them opens new dimensions to problem-solving strategies.